We're going to go over solving systems of linear functions. First, we're going to talk about the types of solutions. So if you are asked how many solutions does the system of functions have, you have three options. There's either one solution, and if there is one solution, that means that the two lines intersect. That also means that the lines have different slopes. Another option is to have no solution. If there is no solution, that means that the lines are parallel. In other words, they have the same slope. And finally, you can have infinitely many solutions. And this means that the lines are the same. So what these look like on a graph, for one solution, if they cross, that means that the two lines simply intersect one another one time. Let me make that a little bit more bold so you can see. The point where the lines intersect is the solution. If the lines are parallel, that means that they never intersect, so there is no solution. And if there are infinitely many solutions, that simply means that when you graph the lines, they are the exact same line. So if this first line that I drew in pink overlaps another line, so if those are the same line, then there are infinitely many solutions because they have all points in common. There are three methods to solving a system of equations. The first two ways we'll talk about are by hand. So you can solve a system by elimination, and you would only need to do that if you are working by hand, meaning you do not have access to Desmos or calculator. The second method is called substitution. Again, this method is done by hand if you don't have access to Desmos or calculator. And finally, graphing is the third way. And to graph a system of equations, you would need Desmos or a calculator. So now let's look at some examples of solving systems by hand. We'll do elimination first. So we have a system here of two linear equations, and we need to use elimination to solve them because they are both in standard form. So notice that both of these equations are in the form ax plus by equals c. Now, to eliminate one of these variables, that means that the coefficient of the x variables or the coefficient of the y variables need to match. So the easiest way I can make variables match is if I multiply one or both of the terms so that the coefficients become the same number. The easiest way to get this current 1 that's in front of the x on the second equation is to multiply this entire equation by 2. So I'm multiplying by 2 on the left and 2 on the right because I want to turn this 1 into a 2 so that these match. And the easiest way to do that is to multiply 1 times 2 gives us a 2. So now I just need to rewrite these to keep things organized. So I'm going to rewrite 2x minus y equals 12 and then simplify this second equation. So we need to distribute 2 times 1x and 2 times 3y. So that would be 2x plus 6y equals, and then we have to multiply -1 times 2, which is -2. So this is our new system. They are equivalent systems. We just made the variables of the x terms, we made them match. So now I can eliminate the terms with the x variable by subtracting, since 2 minus 2 is 0. So the process of elimination, your goal is to eliminate one of the variables. So if I subtract 2 minus 2 becomes 0, and if I subtract those, I also have to subtract the other terms as well. Now I'm subtracting straight down. So 2 minus 2 is 0. Then I have -1y minus positive 6y, which is -7y. Bring down the equal sign, and then we have 12 minus -2. So since I have minus a negative, the operation is addition, and that is positive 14. Finally, to solve for y, we're going to divide by -7 on both sides. So we get 1y, or just y equals -2. So this is part of our answer, but it's not the final answer. When we're solving a system, we're looking for a point of intersection, or an x and a y. So we found y, and we can plug this in. We can plug in -2 for y in one of the original equations. So it doesn't matter which original equation you pick. I will just pick the first one for no good reason other than it's the first one. You could pick the second one and you should get the same answer either way. So this was our original equation. I'm going to plug in -2 where this y is. So I'm going to have 2x minus, and now I'm plugging in -2 for y. And simplify until you have solved for x. So this is 2x plus 2 equals 12. Subtract 2 on both sides, and we get 2x equals 10. Divide by 2, so x equals 5. So we have our two pieces of the solution. The solution is always a point. So let's see, our solution is always x comma y, a point. So our solution is now let's move on to substitution. Substitution is the process of replacing one variable with another expression. So we have our two linear equations here, and one of them is already solved for. So the equation x equals -1 plus y already has the variable x by itself. So in one of the equations, one variable is solved for. And that just means x equals, y equals, or any variable equals something. So we have x equals, so we can replace x with this expression. So the x in the first equation is going to be replaced by -1 plus y. So let's see what that's going to look like. So I'm going to take this first equation. We have 3x. Now instead of writing x, I'm going to write the thing that x is equal to, which is -1 plus y. And then I finish rewriting the rest of that equation. Now it's just the process of simplifying and getting y by itself to solve for y. So we need to distribute 3 times -1, 3 times y, and bring everything else down. Now we are combining like terms, so we have positive 3y and -2y. Since they are like terms, we can simplify by combining them. So the -3 will stay, and we will add positive 3 minus 2, which is positive 1. And we don't have to write the positive 1 in front of that y, but it does help clarify how we got there. So now we need to get all constant terms away from the variable. So we're going to add 3 on both sides. And now I'm just going to write y instead of 1y equals -5 plus 3 is -2. So this is part of our solution. Now, just like in elimination, since I have one of the variables solved for, I have a number that is equal to that variable, I can plug this in for y. Okay, so this time I'm going to pick the second equation, x equals -1 plus y, and I'm going to plug in -2 for y. You could have picked the first equation. I just picked the second one because now we're trying to solve for x, and x is already by itself in this equation. So x equals -1 plus -2 is -1 minus 2, which is -3. So this is the second piece of our solution. So the whole solution itself, let's see, I'm going to move this over and kind of let you see that I plugged in -2 for y right there. So our whole solution, which is always an x and a y, we can write it as a point, is -3, -2. It's very likely that if you are asked to create a system of equations, that it will be a calculator active portion of a test or assessment. So when we are creating systems, typically you will have the option to graph them in order to solve them. So we're going to kind of combine these two skills of creating systems and solving by graphing into one example. With this example, we have a word problem where Books A Million sells new books. Paperback books cost $2 and hardback books sell for $4. The store sold 65 books and made $180 from the sale. How many hardback books did the store sell? So from here, we're going to stop and take a look at things that we know from this given information, and then look at our question and really detail, write out in detail what we need to find. So we know a few important pieces of information. We know that there are paperback books that sell for $2 each. And since we are solving a system, we can tell from the setup of this word problem that it will be a system of equations. So we need to assign a variable to each item. So paperback books, we're going to call those X, and they are $2 each. Hardback books are $4 each. We're going to call those Y. We also know the store sold 65 books. It doesn't say that it sold 65 of just one type. So we can identify that this is 65 books total. So that's 65 books including paperback and hardback. And finally, we know that they made $180 from the sale. So the total is $180. Now, let's look at what we need to know. We need to know how many hardback books did the stores sell. So what is the number of hardback books? That's what we're looking for. And the number of hardback books, we identified that those are the Y variable. So we need to solve for Y. We need to find Y in our solution. Now let's organize and start solving this system. Okay, from the things that we know, we can say that $2 per paperback plus $4 per hardback was a total of $180. So this equation is dealing with the money aspect of this problem. Now the only other number that we have not used yet is the 65. So we have to consider if the store sold 65 books where some of them were hardbacks and some of them were paperbacks, so X plus Y is a total of 65 books. So this is dealing with the actual number of items themselves. Now, let's look at how to solve this. So I'm going to pull up Desmos and type in these two equations. So we have 2x plus 4y equals 180. And x plus y equals 65. So notice I don't see anything on my graph right now. I'm going to need to zoom out. So when I zoom out and I'm looking at these two graphs, I need to zoom in to where the red line and the blue line intersect. They intersect, or they cross over one another at the point 40, 25. So this technically is the solution to the system. However, we just need to know how many hardback books were sold. So since this is our X comma Y, X was paperback, Y was hardback. So this tells us that 25 hardback books were sold. So that is our final